In this video, we will learn about the Cahn Ingold Prelog designation of enantiomers, the R and S designation system. Let's start our lesson today with the term we learned in the last lecture, enantiomers. So when a molecule is chiral and it has one non-superimposable mirror image, that molecule is called its enantiomer, and they are enantiomers of each other. And remember that the differentiating feature of enantiomers is that at the chiral center, the various bonds that are coming out of it are oriented in different ways. As for example, last time we looked at amphetamine. At this carbon, there are 4 different groups coming out of it, so therefore it is a chiral center. Now, we also mentioned that the easiest way to draw the enantiomers is to basically switch at the chiral center the wedge and dash structures. So if we had the methyl group as a wedge coming out, then if we draw it as a dash going away, then you would have your enantiomer. Now keep in mind that that only works if indeed you have that chiral center. So for example, in this molecule, we have the chlorine coming up as a wedge. If we just drew it as a dash, it will not work. So in this case, these are not enantiomers because you do not have a chiral center. Right? So in fact, these two molecules are identical to each other. Prove this yourself. If you flipped one molecule like a pancake, you will get the other. For example, if you took the molecule on the left where the chlorine is coming out at you and flip it like a pancake, then the chlorine that's coming out will now be the chlorine that's going away. And so you would have the exact same molecule as your molecule on the right, and which is why they are identical molecules. So just be careful of that. So let's go back to our example of amphetamine. So these two molecules are enantiomers of each other. And remember, enantiomers means that they are separate molecules. They have different identities. But in fact, these two molecules are both called amphetamines. So how do we tell them apart? We need to have a system that designates one enantiomer versus the other. In some cases, this is very important. For instance, one enantiomer could be a helpful drug, whereas its enantiomer could be poisonous. In the case of amphetamine, the structure on the left is called dextroamphetamine, is the active ingredient in a lot of ADHD medication. It is a central nervous system stimulant. Its enantiomer has a similar molecular function, but actually has a little bit less effectiveness. In any case, we need to be able to give them different names because they are, again, different molecules. And it turns out there are different ways to differentiate these two molecules, but in this video, we will learn of a systematic way to designate and differentiate them. And it's a system named after 3 chemists, Cahn, Ingold, and Prelog. The first step in this designation system is to identify the groups that are coming out of the chiral center and prioritize them. And the groups are prioritized based on the atomic number of the atoms connected to the chiral center. So let's take a look at an example to make this point clear. Right, so we have here a molecule with a chiral center that has 4 groups coming out with different atoms to make this a simple and straightforward example. So the atoms that we are considering is the chlorine, the hydrogen, the oxygen, and the carbon. So among these 4, which one would have the highest priority? Which one has the highest atomic number? With atomic number 17, chlorine would be the highest in priority, followed by oxygen as atomic number 8, followed by carbon as atomic number 6, and lastly hydrogen as atomic number 1. So we always have to list the 4 groups in terms of their priority ranking. The second thing we have to consider in this system is that the group number 4 must always be in the dashed position. It must be going away from us. And if it isn't, you must rotate the molecule. So for now, let's just see how we can rotate this molecule visually. Notice that it is in the front, it is facing us, right? So in order to rotate this molecule to be in the back, you would have to do a 180 degrees rotation. Hydrogen will be in the dashed position. And the last step here is to determine the sequence of the groups 1, 2, and 3. Once you have the 4th group in the back, you just count 1, 2, 3. And depending on the direction of that circle that you draw, you will designate it either as an R or an S. R stands for clockwise, for the Latin word rectus for right, and S is counterclockwise, which stands for the Latin sinister for left. Right? So in this case, if you count from 1, 2, 3, you make a loop, you make a circle that goes in the counterclockwise direction. So in this case, we can say that chiral center is designated S, or we can say that this whole chiral molecule is the S enantiomer. So that's the basic framework of the Cahn-Ingold Prelog designation system. We will now take a look in more detail at some more nuanced cases that might give you some trouble. Okay, now let's take a closer look at assigning priorities. This is the first step in your designation. Let's go back to our original molecule, the amphetamine, and see how we can assign priorities to the groups coming out of the chiral center. So in this molecule, the highest and the lowest priorities are pretty straightforward. The nitrogen has the highest atomic number, so that should be ranked as number 1, and the hydrogen the lowest, so that should be number 4. The other two positions are a little bit different and we haven't seen them so far. We have to take a look at them in a little bit more detail because it turns out they are both carbons. So if they are both carbons, what would you do? So if you have a tie in the first point of contact, then you would just have to compare what other atoms are connected to that tied atom. So the carbon on top is connected to another carbon and 2 hydrogens. And then so you would list those connections starting with the atom with the highest atomic number. So in this case, it is connected to a carbon, a hydrogen, and a hydrogen. Whereas this carbon here on the bottom, the methyl that's coming out, is connected to 3 hydrogens. So simply list them out, and then you would just compare side by side. You have 3 rungs of comparison here, so you just go down one at a time until you find a tiebreaker. In this case, it's quite simple. The first comparison we see here can already differentiate for us. So carbon has a higher priority than hydrogen. So therefore, this carbon on the top here has priority ranking number 2, whereas the methyl group, the carbon on the bottom, would be the 3rd in ranking. All right, so let's just go ahead and finish this example. We already have the group 4 as a dashed structure. So all we have to do now is connect and count 1, 2, 3. It is going in a counterclockwise direction. So that amphetamine structure is indeed an S designation. Let's go ahead and do another one. So take a look at this molecule. Can you find the chiral center? Hopefully you were able to see that there is indeed a chiral center because there is 4 different groups coming out of that carbon, including that hidden hydrogen. So let's assign our priorities here. So again, in this case, the easiest one to assign is this hydrogen, the lowest ranking, number 4. Now the other 3 is a little bit tougher, right? You have 3 carbons, so you have that tie again. So again, to break the tie, you just have to list out what else is connected to those carbons. So starting from the carbon of the carbonyl, notice that it is doubly connected to that oxygen. When something is doubly connected, that means in your priority ranking, you list them out twice. So it will be oxygen, oxygen, and carbon, right? How about the carbon of the alkyne? Notice that that carbon is connected triply to another carbon, so we just list them out as carbon, carbon, carbon. And lastly, the carbon on the bottom is connected to a carbon and 2 hidden hydrogens. All right, so go ahead and just compare them. So the first point of comparison here, we have here oxygen, carbon, and carbon. So oxygen already is the winner there. So this carbon of the carbonyl is group number 1 priority. Since the other 2 groups are still tied with that first rung of comparison, we then have to go on to the next one, which is a comparison between a carbon and a hydrogen. So therefore, the top group, the alkyne group, will have higher priority because the carbon is higher than a hydrogen. So that alkyne group is priority number 2, and that alkyl group in the bottom is priority number 3. Again, let's just finish this example. We have already the 4th group in the back, so we do not need to do any manipulation of this molecule. We just simply count 1, 2, 3, and see which direction that is. That is clockwise, so that is indeed an R designation. All right, the next point we want to take a look at in detail is the second step, where sometimes we do not have the lowest ranking group in the dash position going away from us. So therefore, we have to rotate the molecule. In the first time we did this, I kind of did it mentally where we kind of flipped the molecule so that the fourth group is in the dash position. That's not the easiest mental acrobatic. So here's a trick on how to do that more simply and even faster. And so in this section, we'll take a look at how to easily rotate a molecule. And to illustrate this to you, let's first take a look at a simple example here. I have a molecule where I've already designated the priority groups, and I put the lowest ranking already in the back to make it easier for us. As is, what is the designation of this molecule? If you go from 1 to 3, that's a S counterclockwise designation, right? So what happens if we were to switch to two of the groups, switching group 2 and 3? What is the designation of this new molecule? 1, 2, 3. It is now clockwise, right? So our first conclusion here is that whenever you switch two groups of a chiral center, you will get the opposite designation. If you're an S, you become an R. If you're an R, you become an S. And it actually doesn't matter which two groups you switch, that will always happen. Let's do that one more time then. This time, let's say we switch groups 1 and 3. What would we get? Okay, so this time we have 1, 2, 3 going this way. It is now counterclockwise. So we've switched from an R to S because, again, we have swapped one group. And so what is the larger implication of this? It turns out that anytime you do one switch, you get the opposite configuration. But if you do two swaps of any two groups, you will get the same designation back. You will get the identical molecule back again. So this is a very simple trick you can use whenever you want to put the fourth group to be in the back. Just remember to do the swap twice so that you do have the same molecule back again. So let's go ahead and see how this looks like in my molecular set here. And so in this molecular set, the white ball is hydrogen, the green is chlorine, red is oxygen, and the black is carbon. So take a look at that. And does that make sense that they are ranked in the priority that they are? All right, so again, we have this first molecule. Let's count 1, 2, 3, so that's counterclockwise. So let's switch these two at position 2 and 3. Right? So again, that's the molecule as you see as drawn. I swap those two. Let's hold it where hydrogen is away from us. And let's count 1, 2, 3. It is now clockwise, the R. Now let's switch, like I said, the number 3 position and number 1 position. So that's how the molecule is drawn, like that. And let's hold hydrogen facing away from us and count 1, 2, 3. Right, so that is S. Right, so hopefully you are convinced. If not, you can just play with this with your own molecular model set to prove yourself that if you do two swaps, you get the same molecule back. Now let's see the usefulness of what we just learned based on this molecule that we did earlier. Remember that the ranking for this molecule would have chlorine as number 1, this oxygen as number 2, this carbon as number 3, and this hydrogen as number 4. Now notice again that the hydrogen is out in front, so we can't designate it until it is in the back. Let's use the trick we just learned, and remember that we previously determined it to be an S designation. Okay, so the first thing again is to do swapping of two groups, and we need to do it twice. So I can choose these two to swap, and these two to swap. So let's do the bottom first. Notice that the 3 was on the left, now the 3 is on the right, and the 2 is on the left. And on the top, the 4 is now in the back, and the 1 is on the right. Okay, so from that, what is our designation here? 1, 2, 3. That is indeed an S. Right, so you notice how I just swap any two groups. Let's do that again. I want to be able to convince you that we can do this on any two groups and it will give you a good answer. What if we decided to swap this group? So this is 1, this is 4, this is 3, and this is 2. And then swap this group. Again, because we said as long as we swap any two groups, in this case, I'm swapping a group that's already swapped once, just to illustrate that it doesn't matter. Okay, so what is the designation here? 1, 2, 3. that again is indeed an S designation. So there we go. So again, to summarize, switching any pair will give you the opposite configuration, but then if you switch any pair after that, again, it will give you the opposite configuration again, which is basically the original configuration. All right, so you hopefully see that how useful that is when you have a structure where the fourth group is not in the dashed position. So here we have a molecule called 2-butanol. The nomenclature of this, naming of this molecule, we won't get into in detail, not just yet, but let's for now just know it's called 2-butanol. But we need to be able to also identify if this is an R or an S molecule because it does have a chiral center. Right? So if you were given this molecule, how would you go about to designate the R or S configuration? Hopefully you do recognize immediately that there is a chiral center, and that chiral center has a hydrogen that's coming out. And hydrogen is our lowest ranked priority group, so we need to somehow put it into the back, right? So we need to do some swappings. But before we do that, let's go ahead and just number our groups first. So the alcohol is number 1. This carbon over here is number 2. Convince yourself that that is number 2 and the methyl group is number 3, and therefore this hydrogen is number 4. Again, we need to do some switching in order to have number 4 be in the back. All right, so 2 and 3 swap, so this is now 2 and this is 3. 1 and 4 swap, so this is 1 and this is 4. So since 4 is in the back, we can go ahead and do our counting of 1, 2, 3. That is in the S configuration because it is counterclockwise. So there you have it. That trick helped us make this designation very, very quick. Okay, and before we go on here, since it is a chiral molecule, we would need to give it a special name. We just know that it is no longer just simply 2-butanol, but we also know that the chiral center has an S configuration, so we simply put an S in front of the name in the parentheses. So this molecule is called S2-butanol. If it was the opposite enantiomer, you would call it R2-butanol. So there you have it, how you would name a molecule specific to a certain enantiomer. Now, since we're on this naming topic, let's go ahead and take another example here. Again, we haven't learned how to name alcohols yet, so I would give you this. It's called 3-methyl-2-pentanol. If you were asked to write the name of the specific enantiomer with respect to the chiral centers, how would you write this? Notice there are 2 chiral centers in this molecule, and I'll leave it up to you to prove to yourself, but the first one is an R, and the second one is an S. And according to this nomenclature, you would count this as in the backbone of this molecule. The position here is 1, 2, 3, 4, and 5, hence the pent in there. Okay, so in order to tell the reader that at position number 2 it is an R configuration and at position number 3 it is an S configuration, when you have multiple chiral centers, you must be explicit in telling the audience which carbon is chiral and what is its designation. So in this case, we have the carbon number 2 and the carbon number 3 as chirals. So we say at carbon number 2, it is an R, so we say 2R, comma, and carbon number 3 is chiral, so we say 3, and it is an S configuration, so we say 3S with a dash in between. So the whole name of this molecule is 2R3S, 3-methyl-2-pentanol. Let's go on to another example. What about this structure? How would you designate the chiral center here? When you look at this molecule, you should first recognize that it is a Fischer projection. So therefore, you have to recall back on how Fischer projections, what these lines represent. Remember, any horizontal line in a Fischer projection means it's coming straight at us. And any vertical line means it's going away from us. And then you can take any 2 of these adjacent groups and make them flat. So I'm just going to go ahead and make these 2 flat. All right, so before we do anything further, let's go ahead and number our priority groups here. So we got, this is number 1, the ethyl group is number 2, the methyl group number 3, and this hydrogen number 4. Again, in this case, our fourth group is not in the dash. It needs to be, so we need to do a flip. So I'm going to go ahead and swap these two groups and swap these two groups. Right, so you got the fourth group here and the second group here. 1 and 3 are swapped also. Fourth group is now in the back, so we are ready to go to count our circle. So 1, 2, 3, that's S because it's counterclockwise. It takes a little bit more steps when the Fisher projection is given to us, but we are capable of doing that. All right, let's do one more example. Let's say you are talking to a colleague and you drew a molecule that looks like this, while your colleague drew another molecule like this. And you notice that these molecules look very similar because of the groups that are coming out of the same chiral center. So the question is, are these molecules that you're drawing enantiomers of each other, or are they actually the same molecule? So the easiest way to do that is simply designate the R or S configuration of the chiral center. If they are both the same designation, then they must be the same molecule. So again, let's go ahead and count our priorities here. 1 is a chlorine, 2 has an oxygen, 3 is the methyl group, and lastly 4. Again, that's not going to be great for us because we need the fourth group to be away. So go ahead and do a swap of these two and a swap of these two. So we got 1 and 2 as swapped, and 3 and 4 swapped. 4 is going away from us finally, so this we figure out is an S designation. What about the molecule on the bottom? Lucky for us, a molecule on the bottom already has the fourth group going away, so we probably don't need to change anything here. Let's count the rest of this molecule here. 1, 2, and 3. It is also an S designation. All right, so if these two molecules has the same group coming out of the chiral center and they are indeed the same S designation, therefore, you and your partner have drawn the same molecule. You are talking about the same molecule, the S enantiomer of this molecule. All right, so hopefully you will get some more practice on your own and to master the Cahn Ingold Prelog system of designating the configurations of chiral centers.